Hello guys, so this is lecture 15 and we continue to study spectral theory. So 15.1, today we will talk about algebraic versus geometric multiplicity. So let me remind you the setting. So we have a vector space V, and we have a linear map from V to E, which we also call linear operator. And then, so if lambda is some number inside our field, then we can define V lambda, which is the space of all vectors V in V, such that L of V equals lambda V. So this is what's called lambda eigenspace. So this lambda eigenspace consists of all eigenvectors with eigenvalue lambda, and I remind you that it's very easy to see that it's actually a subspace of V, because when you sum two eigenvalues you get an eigenvector. If you sum two eigenvectors you get an eigenvector, and if you scale an eigenvector you get an eigenvector. So that's a lambda eigenspace, and dimension of the space is called the geometric multiplicity of lambda, and we will denote it by something like, say, G sub lambda. By the way, here is a second cat. So finally, yep. Okay. So G lambda is this dimension. And we have already seen that in some way eigenvalues and eigenvectors are related with roots of characteristic polynomials. Namely, I remind you that eigenvalues of a linear map are roots of characteristic polynomial. So each root of a characteristic polynomial has multiplicity. So definition A sub lambda, which is also called arithmetic multiplicity, algebraic. I meant algebraic. Algebraic multiplicity is the multiplicity of a root lambda of the characteristic polynomial chi sub L. So here is an example. So for instance, you can take a matrix like 1, 1, 1, 0, 0, 0, 0, 0, 3. So characteristic polynomial is, since it's very easy to see, it's 1 minus t squared times 3 minus t. So eigenvalues are just 1 and 3. And arithmetic multiplicity of, let me say, a1 equals to 2, just because it goes here with power 2, and this arithmetic multiplicity of 3 is 1. So when we look at geometric multiplicity, we know that geometric multiplicity of 3 is definitely 1, because so by this theorem it has so why? Because actually the only eigenvectors with eigenvalue 3 are these guys, 0, 0, and something here. And if you look at G of 1, that's actually also 1. And the reason is that the only eigenvectors are eigenvalues x, x, 0. So if you just solve the system of equations, you will immediately see that these are the only eigenvectors. And so though the algebraic multiplicity is 2, the geometric multiplicity is smaller. So so actually we have just 2 linearly independent eigenvectors for these 2 eigenvalues, so the whole space has dimension 3. So I want to prove the following very important theorem. So theorem So there are several statements. So the first statement is that eigenvectors are corresponding to different eigenvalues are linearly independent. So if you have eigenvectors whose eigenvalues are different, they are linearly independent. For instance, these two guys are linearly independent. So the second statement is just a corollary, is that if you sum up all these dimensions of all this V lambda, then this number is less or equal than dimension of V. And this just follows basically, sum goes over all lambda in F. And this is just a corollary of 1, and we will see it very simply. And finally, part 3 is that this dimension G of lambda, which is this dimension of V of lambda, is less or equal than this algebraic multiplicity A of lambda. So here we see the geometric multiplicity of eigenvalue 1 is equal to 1, though algebraic is equal to 2. And that's always the case, as geometric is less or equal than algebraic. So unfortunately, or maybe fortunately, that makes the subject more interesting, that's not true that these guys are equal to each other. So though you can easily understand all eigenvalues of a linear map just looking at the characteristic polynomial, you cannot understand exactly how big are the spaces. And in particular, it's not true that they always have the maximal dimension, which they possibly might have, being this A of lambda. So if you work over complex numbers, then as we will discuss a little bit later from main theorem of algebra, it follows that your characteristic polynomial can be just expanded in these linear terms with some integer powers, and so you immediately know all arithmetic multiplicities by just looking at the terms and their powers. But it does not imply that you know geometric multiplicities. So actually you don't know exactly how many linearly independent eigenvectors for every eigenvalue you have. This is something which for which you need more thorough analysis to do to understand what's going on. So my goal today is to prove this theorem, and later on we will see various examples. In particular, the most important case is when we have equality here, and this is the next topic, diagonalizable matrices and diagonalizable linear operators. So this we will discuss later, and then we will see a lot of applications of all these techniques. Okay, so let me now start proving this theorem. So proof. So let's start with part 1. So assume that, so let V1 Vk be eigenvectors with eigenvalues lambda 1, lambda k, where this guy are distinct. So let's suppose they are linearly dependent. So suppose they are linearly dependent, and then let's apply the trick we have already done several times. So pick a linear dependence with the smallest possible number of vectors involved. So we have already seen this minimal principles applied, so you can look at all linear dependencies, and of course if you naively you think that the smallest one will involve all k vectors, so x1v1 plus tdd plus xkvk equal to 0. But maybe there is one which involves just, I don't know, k minus 1 of those, or k minus 2 of those. So we'll pick the one which is the smallest in the number of vectors involved. So let's assume that, so suppose it is a1 vi1 plus a2 vi2 plus a k vik equals to 0. And here is a linear dependence between these vectors. So and we know that, of course, if it is the smallest one, we know that a1, a2, and so on, ak are just all not zeros. I mean, if there is one of them is 0, we can just omit this term. Perfect. So then we can apply the linear map L because it's linear, and we get that a1 L of vi1 plus plus ak L of vik equal to 0. But that's really easy to compute because we know that these guys are just rescalings. a1 lambda 1 vi1 plus plus ak lambda k vik, lambda i1 lambda ik equals to 0. So interesting, we have a linear dependence and we have another linear dependence. So okay, perfect. So then we know that clearly so k is greater or equal than 2, because if you imagine that actually the smallest linear dependence is for k equal to 1, it means that one of these v vectors is equal to 0. But we know that so of course we can, so we don't call 0 vector an eigenvector for this eigenvalue. So this is why there should be some other vector. So these vi's are not 0. So it means that k is at least 2. And then what we can do, so we can just subtract from one equation another multiplied by some number. So so this implies that, and then let's take the top equation and multiply it on lambda ik. So we can assume, so then without loss of generality, we can assume that lambda ik is not equal to 0. Of course, it might happen that one of the eigenvalues equals to 0. This is just the one corresponding to the kernel of this map, because this is the one which kills all vectors. But since there are at least 2 of them, we can assume that one of them is not 0, and let's say it's ik. So then we can take another, so we can take this linear combination and take this linear combination. So it's star star, this is star. And then let's consider star minus star times lambda ik minus star star. That's also equals to 0. And what it means that a1 lambda ik minus a1 lambda i1 vi1 plus plus a k minus 1 lambda ik minus a k minus 1 lambda ik minus 1 vik equals to 0. And of course I did it not randomly, I did it so that the last term will be just disappearing completely. So this is linear dependence between k minus 1 vectors, sorry. So this is linear dependence between k minus 1 vectors. But if there exists a linear dependence between k minus 1 vectors, this just implies that all coefficients are 0. So a1 lambda ik minus a1 lambda i1 equals to 0 up to ak minus 1 lambda ik minus ak minus 1 lambda ik minus 1 equals to 0. So just all terms equal to 0. Because we took the one which has the smallest number of possible vectors involved. But of course, since we know that for instance, look at the first term, we know that a1 is not equal to 0, so we can divide on it, and then we see that lambda i1 equals lambda ik. So where shall I write it? So lambda i1 equals lambda ik, and this is a contradiction. So just I mean, you can take any of these equalities, divide by this all AIs, and you get that lambdas start to be not all distinct, and we started with distinct eigenvalues. So this is a very beautiful proof, and this is something to remember. This idea appears in algebra a lot. So you have one linear dependence. You want to show they're linearly independent. You took one linear dependence which had the smallest number of vectors involved. You applied linear map, and using the fact that they are all eigenvalues, you got another one. But then you have the two of them with the same number of vectors involved, and you can cook up of them another one which has a smaller number of vectors involved. And this has to be just 0, 0, 0, because we know that such thing cannot happen. And so all the coefficients, after we subtract, all the coefficients have to be 0, and this is a contradiction. You will see this argument appearing again in Galois theory and in many other mathematical algebraic topics. So that proves part 1, and part 2 is a direct corollary of part 1, so let me show part 2 here. Or actually, let's take a different road. So what we did, we proved, so 1 is proven, and actually then it's very easy to see that 3 implies 2. So why 3 implies 2? Because we know that, so assume we know 3, so assume 3, and then we know that sum of all g of lambda over all possible eigenvalues. By the way, notice that when you sum up over all numbers lambda at all, it's the same thing as summing over only eigenvalues, because, I mean, by convention we put g of lambda equal to 0 for all other numbers which are not eigenvalues, so that's just convenient. So this is less or equal than sum of lambda over f a of lambda. And then, so these guys are multiplicities of some roots. And remember that sum of multiplicities of all roots is less or equal than n, where n is the degree of characteristic polynomial, which is the same as dimension of v. I mean, this is just because if you know that you have your polynomial chi is something like x1, x t minus lambda 1 power a1 to the t minus lambda k power ak, and maybe times some other polynomial r, because you know that it has its roots with some multiplicities, but it might be the case that there is some part which has no roots at all. Then you know that a1 plus and so on plus ak is less or equal than degree of chi. So from this we see that sum of geometric multiplicities is less or equal than n. So 3 implies 2 trivially, but let me also say that actually 2 follows from part 1 as well. And the reason is, imagine you have these different v lambdas, and you can take a basis for each of them. And now consider all this collection of vectors, basis for each v lambda. The number of vectors will be exactly the sum. But on the other hand, it's easy to see that they are all linearly independent, because any dependence between them will lead to dependence between different vectors in v lambdas, and so each of them has to be equal to 0, which cannot happen if you took a basis. So that's why there is another proof how 1 implies 2, which is not using this more complicated statement 3. So now let me prove 3. So now 3. So 1 is done, this is done, and now I want to show 3. So for 3, I need a lemma, and lemma is actually very important and nice lemma in general. So, lemma. So let me just write it maybe symbolically. So if you take determinant of a matrix which has a form A, B, C, 0 equals determinant of A times determinant of C. So what is written here? So there is an idea of so-called block matrices. So block matrices are matrices where you can just draw two imaginary vertical and horizontal lines, so that the matrix is like divided into several blocks. And of course any matrix can be divided like that, but here we assume that one of these blocks equal to 0. So an example of this matrix is the one which appeared before in the example we discussed, this one, 0, 0, 0, 3, 0, 0. So for instance, it is a block matrix where we can make it a block matrix like that. And it has zeros in one of the quadrants. So, and then the statement is that the determinant of such matrix is just the product of two determinants, determinant of A, determinant of C. And interestingly, what stays in B here is not important at all. So another example is that if you just take the matrix 1, 1, 1, 0, from the theorem it implies that determinant is equal to 1 times 1, and then the same whatever number you put here. Of course, that's not particularly surprising because you can do column and row operations to use C to actually just subtract their elements from B and use A in a similar way, and eventually you can just show that using just operations 3 for rows and columns you can erase B or the whole matrix has determinant 0. But we'll prove it in a slightly different way. So this is a very convenient thing to know, because it means that actually if you want to compute determinant using linear operations, you don't need to make it completely diagonal. You can just make it, partially diagonal, and then you split it into parts. So kind of step type matrix. Perfect. So let's prove it. So proof is a little bit boring, but not too terrible. So proof. And proof will imply the statement about geometric multiplicity pretty fast. So for this proof I need a little bit more space, so let me erase what stays to the left. Okay, so proof is a little boring, but not too terrible. So let's take this matrix, and let's assume that we have this matrix, and it is like that. So all these matrices, sorry, I meant A and C are square matrices. So basically this is some number n, this is some number m, and so this matrix is m by m, this matrix is n by n, and this matrix is n by m, but thankfully we are not trying to compute its determinant. And let me call the whole matrix m. So we know that everything here is equal to 0. So what it means? It means that mij, sorry, that's a bad notation. Let me call this matrix X. So we know that Xij is equal to 0 for I greater or equals than n plus 1, and j less or equals than m. So these are exactly these guys. So under this assumption, I want to compute determinant of this matrix X. Okay, so let's just write down formula. So let me do it maybe here. So determinant of X equals to sum over all permutations sigma in n plus m size minus 1 power sigma x1 sigma of 1 to xn sigma of n. I will just split it into parts. Sigma 1 plus 1 to xn plus m sigma n plus m. So and for us it will be convenient to think that monomials in each part are divided into two groups. So there is a left part corresponding to something coming out of the first n rows, and the next part coming from the next m rows. So then we know that some of them are equal to 0. So let's denote this monomial by I know, x sub sigma. This is just monomial without sign. So we know that this x sub sigma equals to 0 if at least one of the terms equal to 0, and this happens if some, so because we know that everything here is 0, and when it happens, so it happens for I greater or equals than n plus 1, and then j less or equals than m. So we need to look just at these terms, only then they can appear here, and they equal to 0 if one of these guys, the second part, is less or equals than, sorry, less or equals than I greater or equals than n plus 1, less or equals than n, sorry. So it equals to 0 if sigma of n plus 1 is less or equals than n, or sigma of n plus 1 is less than n. N plus m is less than n. So if one of these guys is less than n, then we are done and the monomial vanishes. So in other words, x sigma is equal to 0 unless sigma of n plus 1 is greater or equals than n plus 1, and so on sigma of n plus m is greater or equals than n plus m. So, which happens if and only if sigma sends the set n plus 1 to the n plus m to the set n plus 1 to the n plus m. Okay, so but then, of course, we know that sigma is a bijection, so sigma is a bijection of a set with n plus n elements, and we know that if we split it into parts, everything from 1 to n and from n plus 1 to n plus 1, we know that sigma is bijection on this part. So, of course, it has to send the first n elements to themselves as well. Formally speaking, you can say that you know that sigma, so sigma is a bijection of this set. Assume it takes one of the elements from 1 to n here. Then, since sigma is a bijection, it means that this is just a contradiction, because sigma is bijective on this subset, so it cannot send any element of the other side there. So then sigma also sends 1 to n to 1 to n. Okay, so let's denote. It's very convenient to denote, so denote sigma 1 be sigma restricted to the set from 1 to n, so we just look what it does on this set. And sigma 2 be sigma restricted to n plus 1, n plus m. And then you can think of sigma as basically being sort of sigma 1 and then sigma 2. So you just apply sigma 1 to all elements from 1 to n, sigma 2 on all elements from n plus 1 to n plus m, and of course their order doesn't matter. So we will think of sigma 1 as an element of Sn, permutation of the first m letters, and sigma 2 as a permutation of the second m letters. And then clearly the sign of sigma is nothing but the product of signs of sigma 1 and sigma 2. And you can prove it in any way. For instance, if you present sigma 1 as a product of transpositions in Sn, and sigma 2 as product of transpositions with these letters, then sigma 1 times sigma 2 will be a product of all these transpositions, so its sign is the sum of signs. But also you can think of it as just because it's a product inside the bigger set of all permutations. So here is a little ambiguity, because I mean, a priori you can think of the sigma 1 as being a permutation in Sn, or a permutation in Sn plus m, which fixes all the other elements. But the answer still holds, and I will prefer to think of them as permutations of Sn and Sm respectively. So that's why we have, and here of course I think of these guys as being plus minus ones. So now let's look again at this sum. So actually this determinant of x from what we discussed is equal to sum over all these pairs sigma 1, sigma 2 inside Sn times Sm. So we need to take permutation sigma in Sn plus m, which is built out of these two guys. Then there is minus 1 power sigma 1 minus 1 power sigma 2. And then the product of monomials. And we know that all monomials other than z coming from the sigmas vanish. So it means that it is actually monomials are x1 sigma 1 of 1 up to xn sigma n of n times xn plus 1, sigma 1 of n, sigma 2 of n plus 1 to the xn plus m sigma 2 of n plus m. But this is just the product of two determinants. That's just determinant of this part. Let me call it x sub 1, and this part x sub 2. Literally. Just because this is how the determinants will be defined. And you see that basically these terms, all terms where there is at least one element here, they just vanished because of if there is some element here, there will be some element from here as well inside the monomial. So this is the proof, and I hope it is transparent. Please think it through a little bit. And this proves a lemma for us. So now we know how to compute determinants of every matrix built out of these blocks, which is useful. Okay, so our next goal is to show that geometric multiplicity is always less or equal than algebraic multiplicity. That becomes pretty straightforward now. Okay, so now we finish. Theorem part 3. So, okay, so the statement is that for every lambda in F, geometric multiplicity of lambda is less or equal than arithmetic multiplicity of lambda. So, why this is the case? Okay, so let's pick some bases, v1 up to vg, of v sub lambda, where g is this number, and extend it to the basis v1, vg, vg plus 1 up to vn of v. So every basis of a subspace can be extended to the basis of the whole space. So then let's look at L in this basis. And then let's look at the matrix of L. So matrix of L will look like that. So we know that vector v1 is going to lambda times v1. So v2 to lambda times v2, and so on, vg to lambda times vg. So we have basically a block on top, which is just diagonal matrix. And this is j by j block. And here we have all zeros. And here we have something, and here we have something. So this matrix is exactly like the matrix in the theorem, so it's a block matrix. And so if we take m of L minus t lambda, minus t times 1, so the one which appears in the characteristic polynomial case, we will see here lambda minus t to the lambda minus t something 0 something. And so let's call it, this will be L1. So this block will be L1 and this block will be L2, exactly like in the notation before. So then actually we know that characteristic polynomial of t will be product of two determinants, and this is lambda minus t power g, because this is just diagonal matrix, everything else is 0, times something, this determinant of this part L2, L2 is this one, L2 minus t, which is some polynomial. And so it means that multiplicity of lambda is greater or equal than g. And so it means that this a of lambda is greater or equal than g of lambda, just because we found that our polynomial is divisible by this lambda minus t g times power g. This proves this theorem. Okay, so let me roughly describe to you what happens next. So in the next part of the lecture, we will talk about diagonalizability. So this is the case when actually for every lambda, arithmetic and geometric multiplicities agree. And what it means that, as we will see, that actually a linear map has a basis consisting of solely eigenvectors going in different directions, all linearly independent. And on this basis, matrix is just diagonal. So it is very easy to think about how to take powers of a matrix and so on if you have a basis consisting of eigenvectors. And unfortunately, that's not always the case, and this is the case precisely when always arithmetic and geometric multiplicities agree. So, but if you take a random matrix with complex coefficients, that's always true. But for some matrices, if you specifically adjust parameters very badly, this will start to be wrong. Then there are ways to treat it. There is so-called Jordan normal form theorem, which tells you that you can still simplify a matrix a lot and write it down as some collection of blocks, basically, which will be slightly more complicated than this diagonal guys. But this theorem is much harder, and I'm not going to prove it, though I will formulate it maybe. So, and then I will show you a few applications of this diagonalizations process, how one can compute powers of matrices, how one can apply it to, say, solve recurrence relations, and so on. And this will be the end of the spectral theory topic. So basically, you see that this proof is already a little bit involved, and if you want to understand better basically why this arithmetic and geometric multiplicities are different, and how to add some more generalized notion of eigenvectors to make them equal to each other, that's whole very interesting, but this is not this is beyond this course. Okay, next we do diagonalizability.